All right, as announced at the end of last week, we are going to jump straight to Chapter 8. We're just skipping the rest of Chapter 7. There will be no test because it was the review. Speaking of which, if you didn't turn in the review, highly recommend doing that. Because it'd be a real bummer to have 0 as like half your grade.
Oh, that's a test grade, right?
Yeah.
Got it.
Oh my word. Anywho, so make sure your review B gets turned in. That is very important because, again, you know, test. Test grades are important. 0 as a test grade would be a real bummer. It would make it basically impossible for you to pass this class. So, yeah, seriously. Well, I mean, how dumb would you have to be to not turn in a test? I say as half the class hasn't turned it in yet. Anywho, y'all take that how you will. I don't care. 8.1, Introduction to Probability, because we need to get into the next section. Honestly, this is more fun. Anyway. You haven't even talked about probability yet. No. You haven't had probability with me yet. Okay, give me a fighting chance. No, give me a fighting chance. Give me a fighting chance. Alright, we're going to start talking about statistics. Now, cool thing about the history of statistics, statistics was actually created by a Christian whose entire goal was to prove to his friends that they were being idiots and wasting their money by gambling. That's the entire history of statistics. Was someone developed an entire branch of mathematics to prove to his friends that they were going to lose money every time. I mean, this was before the internet, so like, eh. Alright, and actually, a lot of the studies that came out of it have since been, well, extremely helpful to mankind. So, you know, good thing. But yeah, I don't know, I always find that mildly amusing. Yep. Alright. Yeah, you have better odds of being struck by lightning 40 times in a row than winning the California lottery. Yeah, it doesn't say it won't happen. It's saying you personally have better odds of getting struck by lightning 40 times in the same spot over and over again. No? But it's possible. Okay, y'all are misunderstanding probability already. Here we go. I would buy a ticket. Yeah, anyway. For the record, I don't condone gambling. But anyway, we will get into that in a minute. Alright, so listen up. Make sure you're not talking. Flipping a coin has a long history of being used to randomly select between possibilities and to settle disputes. Although it is typically thought of today as heads or tails, the ancient Romans, who were among the first to flip coins, called it ship or head, as their coins had a ship on one side and the emperor's head on the other. The probability of an event occurring is whether or not you're on the PowerPoint. Alright, anyway. Is the event's likelihood. When a fair coin is flipped, and that is key. Actually, U.S. quarters are slightly unfair. It's actually a 49 to 51 probability. We'll talk about that more later. But when we say fair coin, we mean perfectly balanced. And you can't say that without saying as all things should be anymore, but moving on. It's perfectly balanced, so you actually have a 50-50 chance of getting heads or tails. When a fair coin is flipped, each side has the same chance of landing up. Both heads and tails have a probability of 1/2 because there's 2 possible outcomes, heads or tails, and then whichever one you're looking for is one of them. Does that make sense? So, you know, if you call heads, then you have a 1/2, 1 in 2 probability that it will land on heads. Otherwise, it will land on tails. Does that make sense? Okay. When outcomes are equally likely to occur, the formula for the probability of a single event may be used. It's shown on the screen. To find the probability of a single event, write a fraction in which the numerator is the number of outcomes that satisfy or match the event, and the denominator is the total number of outcomes in a sample space, the list of all possible outcomes. Now, very quickly, the outcome satisfying the event is often called in statistics a favorable outcome. That has nothing to do with it being a good thing. It just means it's what you're looking for. Okay? Let me explain. When we give cancer rates, or the cancer probability, the getting cancer would be considered, and I hate saying this, but it would be considered the favorable outcome. It's not what you want to happen, it's what you're looking for. Does that make sense? Okay? So it doesn't necessarily, if someone says it's a favorable outcome, they don't necessarily mean it's a good thing. It just means that's what they were searching for. Does that make sense? Okay, so it can be used to reference something else like that, and I don't know why I always pick on cancer, but like it's really easy for like everyone to recognize that's a bad thing. So, yeah, car accidents is another one. It's just one of those. It's one of those terms that like it just came about, and then like Oh, maybe we shouldn't have used the word favorable, but it's too late now. So just as a heads up, okay, it's one of those. Favorable does not mean good. It just means what you're looking for. In probability, an event is a group of one or more outcomes. For example, when rolling a six-sided number cube. Okay, seriously, can we not just say die? Because that's what it is. Six-sided number cube. Yeah, yeah. It's die. We have them in board games. Like, just call it what it is. By the way, singular of dice is die. Just as a heads up, you're gonna hear me say die. I do mean like the thing you roll, not telling anyone to die. To be clear. All right. So the notation P event is a shorthand way to say the probability of an event. The probability of rolling an even number would be represented as P even. To satisfy the formula, or using the formula for probability, P even would be 3 over 6 equals 1/2, since there are 3 outcomes that satisfy the event, 2, 4, and 6. Does that make sense? Out of 6 possibilities. You always reduce. Always. Okay. Yeah. No? Alright. Finding the probability of a single event. First of all, you determine the number of outcomes that satisfy the event. Count up all your things that are what you're looking for. Again, count up all your favorable outcomes, whether or not they're actually favorable. All right. Then you determine the total number of outcomes in the sample space, and then you simply put it over itself, or put the thing in the fraction and reduce. Make sense? Okay, let's look at an example. Jerry has a bag of colored candy that contains 3 red, 1 orange, 4 yellow, 5 green, 2 blue, and 5 purple candies. If you stopped reading at some point, don't worry, I don't blame you. Okay, just bear with me. Find the probability of randomly drawing a green candy from the bag. So, Okay. We're told to express the probability 3 ways. I'm going to show you guys how all those work. So, first of all, as a reduced fraction. So, first of all, how many green? 5. Okay, and then we look at how many total. Okay, so what's 3 plus 1? 20. 3 plus 1 is not 20, Bella. Alright, 3 plus 1 is? Plus 4, plus 5, plus 2, plus 5, 20. So 5 over 20, which is what? 1/4. Because I'm showing how the math works, it's an example. Alright. So it's 1/4. What is 1/4 in decimal? 0.25, so that's it represented as a decimal. And then finally, as a whole percent. So 25%. Good. Does that make sense? Pretty easy? Well, I mean, close. There are some more rules. We'll talk about it in a minute. After some candy was eaten, Jerry's bag now contains only 3 red, 5 green, and 2 blue candies. When the probabilities of randomly drawing each of the individual remaining colors are found, 2 important properties of probability can be seen. They show you those examples there. First, notice that every probability must be between 0 and 1. Probabilities must be between 0 and 1 or 0% and 100%. Okay? You cannot have probabilities over 100%. This isn't normal percents. Okay? Normal percents, you can have 120% of something. That's fine. Not in probability. In probability, you have to be between 0 and 100. Otherwise, you didn't count all your possible outcomes. Does that make sense? There's something you didn't account for. Does that make sense? Like, you have to account for everything. Events that are impossible have a probability of 0. Because no yellow candies remain, the possibility of drawing a yellow candy is now 0 or 0%. An event that is certain, or it must happen, has a probability of 1. Notice that the probability of drawing a red, green, or blue candy in this modified problem is now 1, since those are the only remaining colors. The sum of all the... Whoops, I forgot it was still on the slide. The sum of all the probabilities of all outcomes in a sample space is 1, or 100%. Okay. Now, practically, it actually gets a bit messier than this. Okay? We consider mathematically for things to be impossible once they're below the fraction 1 in 10 to the 50th power. Okay? Anything below that is considered scientifically 0. Okay? Because there's always that 1 in the, whatever 10 to the 50th power is, chance that it might happen. Okay, but at 10 to the 50th is where we draw the line. This is kind of a sidebar. This is not in the book. Okay, but the reason I bring this up, does anyone know the odds of life occurring naturally from non-life? Not quite 0. If only it were so good. There's a lot of zeros. Okay? One in 10 to the 40,000th power.
Wait, but then that's impossible.
Yeah, it's considered mathematically impossible. That's the odds of life occurring from non-life. That right there, that number, that alone is enough to disprove chemical evolution.
Wow.
Pure math. Just gone. Cool. Anyway. All right, so just throwing that out there. That number is the odds of all the proteins, everything coming together to even create a single cell organism in like a primordial soup with lightning hitting it. That's straight up the odds of the first life just happening. Anywho, moving on. All right, so probabilities. The probabilities for selecting each of the three possible students are P equals 120, P equals 30, and P equals negative 50. That's not valid because, first of all, you have something over 100. Second of all, you have something below 0. Does that make sense? Okay, so you can't do that. The next one, they show you, that one's not valid because you get 7/5 when you're done. That's a problem. Yeah, you can't have anything greater than 1. Okay, if you add them all up, it should equal 1. Now, real quick heads up, with percentages, because of rounding, you might get like 99 or 101%. For all intents and purposes, we consider that to be equal to 100%. Because we understand rounding is going to happen, but you should be at or very, 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 very close to 100%, or 1. Okay, depending on if you're working with fractions or decimals. Make sense? Okay. Finally, that third example is valid because if we take 0.1 plus 0.7, bless you, plus 0.2, you get 1. Does that make sense? So that is the case for valid. All right, so does that make sense? One last notation you need to be aware of is called the complement. This is not saying, hey, that number looks nice. This is talking about whether or not the completion of your probability. For example, it's everything except what we said. Okay, let me explain. Back to Jerry and his bag of colored candy, because I don't know, why not? This bag of colored candy that contains 3 red, 1 orange, 4 yellow, 5 green, 2 blue, and 5 purple candies. Find the probability of not randomly drawing a red candy from the bag. Now, we represent this with this capital C being raised up there. It's not actually an exponent, it's just the notation. Okay, it means the complement of A. The probability of drawing a red candy is what we would look for and subtract it from 1. Does that make sense? Okay, so first of all, is this the same count? 3, 4, 8, 13, 15. Yes, okay. Making sure it's the same count. So there are 3 red, so it would be 3 out of 20 for the probability of pulling a red candy. Does that make sense? Okay. Well, 1 minus that, or 20 over 20 minus 3 over 20, because common denominator is necessary for subtraction. Okay? And we get 17 over 20 is the probability of not getting a red candy. Does that make sense? Okay? That 17 over 20 is the complement of 3 over 20. It's whatever's left. Does that make sense? Okay. This formula right here is called the complement formula, which makes it like a great quiz and test question. Hint. Hinty, hint, hint. So the complement of 3/20ths would be 17/20ths. It's the probability of something not happening. That's the short version. Say what? Yeah. You just subtract it from 1 because everything has to add up to 1. Or 100% if you're in percents. What? So like fractions, fine. The second that numerator is bigger than the denominator, it's not possible. Because between 0 and 1 is a fractional piece. Does that make sense? A proper fractional piece. Alright. So, quick review questions. First of all, what is the name for any group of 1 or more outcomes? No. Event. Thank you. It's an event. What is the name for the group that includes all possible outcomes? Nope. Nope. Sample space, thank you. Sample space. What is the name for a group that includes all outcomes that do not satisfy an event? Complement. What is the sum of probabilities of all outcomes in the sample space?
Probabilities. What?
Okay, first question, what does sum mean?
Addition.
Yeah, it means the total of. What's the total of all the probabilities? Okay, you guys are like going all around it. Guys, what's the maximum value you're allowed for probabilities? 1 or 100%. That's what they're asking. They all have to add up to 100. What is it, or 1. 100%, 1. I keep just thinking in percents. What is the probability of an impossible event? 0 or 0% if you really want to be extra. Yeah, basically. What is, okay, let me explain what we're doing here, number 6. Oh, right. I was supposed to be filling stuff in. Event, sample space. Forgot I had a slide. Complement. I highly recommend it. This is on page 266. Alright, now let me explain what we're doing in number 6 so you guys know kind of what we're expecting. The probability of flipping tails for a coin flip, we would represent this as P tails. We're not finding the probability, we're just saying how we would represent it. Yes, in theory, it's 1 to 2. In theory. Depends on the coin.
Yeah.
Quarters, I think, are 49.51.
Can you explain that?
Because one side is just slightly heavier.
Why would they do that?
Because.
What's that value?
Depends on the quarter. That's the issue too, is because quarters have undergone several revisions. Like, there's a reason why the Super Bowl, they don't just, like, flip a quarter. They flip a specially made coin that is a perfectly fair coin. Does that make sense? Because when the entire game can be determined by that coin flip at the beginning, it has to be fair. Does that make sense? So, not obviously there's more to it than that, but like a lot of the game gets determined by that. So like you can't have any remote possibility that one side is slanted. So anyway, that's why there's an official coin made every year. It's not just to show off, although that's part of it. All right. So what is the probability of rolling, how would I represent the probability of rolling a sum of 12 on two six-sided number cubes? Say dice, come on. No, we would just say P12.
P12.
Yeah, again, we're only saying how would I represent the probability. I'm not solving for it.
Would it be 12 over 12?
No. It would be 1, because it's not the number, it's how many times the number can appear. It would be 1 over all the possibilities of your dice rolls. I'm not sure it would be 12, actually. Because it's not just,
Two six-sided numbers.
well, for starters, you can't roll a 1, but there's multiple ways you can roll a 6. You follow me? So, like, there's a lot more probabilities there once you add a second dice. We'll talk more about that later. All right, number 8. Dice of plural, die of singular. All right. Probability of not rolling a sum of 12. How would I represent that?
AC equals
Whoops. 12C. That would be how I represent that. We only use A as a placeholder. So the 12 means I'm looking for a 12. The C means I'm not looking for a 12. It means I'm looking for anything but a 12. Why it's a C and why we call it the complement, I don't know. I didn't make that rule. All right. What is the possibility of a spinner landing on an orange area? How would I represent that? P orange.
and the next one PR.
Yep. It's one for you Scrabble people.
Huh?
Scrabble. The two little tiles?
Yeah, that's somewhere.
Yeah. The probability of pulling an R out of the bag.
PR.
Okay. All right. Makes sense? Pretty straightforward? Cool. Let's move on. All right. Number 11. The single coin is flipped. What is the probability of flipping heads? You are correct. 1/2, which is equal to 0.5, which is equal to 50%. You're told to represent it 3 ways in the directions.
Oh yeah, it does. Okay.
So I'm lying to you for no reason. All right. What about tails? Yeah, it's the same. It's literally like copy and paste.
Wait, no, this is a quarter though. You
Okay, for all intents and purposes, in this class, we're going to treat all coins as fair. Does that make sense? I'm just telling you real life ain't that neat. And this is not English class, so ain't is fine. All right, moving on. 12A. All right, looking at the spinner there, first of all, how many square, or not squares, because it's not a square object. How many sections are there? 6. So everything is going to be over 6 to start out with, okay? So for red, how many red squares are there?
1.
So it's 1 over 6, which is 7, 10. Make sense?
How did you know that it's 17?
Because it's 0.16 repeating. And then since there's a 6 after the 6, it's going to go up. Part of the decimal things you should know. Yeah.
Is it one of the things that you don't know how it might not add up to 100?
Yeah, because when you add up rounded numbers like this, you're not going to get 100. When you add up all the fractions, you should get 1. But it's mainly decimals and percents that we have to worry about. All right, how many blue squares are there? Not squares. 3. All right, so this would be 3 out of how many?
6.
What's this reduced?
1
1/2,
half.
which is going to be 0.5, which is going to be, no, it's exactly 50%. All right. How many white squares are there?
2.
So we have 2 over.
6.
We get
1 half.
1/3,
1/3.
which is 0.3 repeating, or 0.33 for the sake of this, whoops, approximately.
Don't you draw a line over it?
We're rounding to the nearest hundredth. All right, so we get 33%. All right, make sense? Cool. This is one of those things that's a lot easier to explain by doing than it is to, like, talk about. So that's why we're doing this. Okay. Oh, that was it. All right, past that, everything else you guys will encounter is basically just an extension of one of those problems. So your homework tonight is to do, the homework. I don't know what else you want there. For homework, you're doing the homework section. Yeah. Most of it's look up bold words. Or, like, make it a percent or something. Like, you guys will be fine. You guys are fine. All right. Again, if you guys need to make up quiz 25, you guys need to come see me in study hall. If you took quiz 25 on Friday, you don't need to see me in study hall. Yeah, that's basically it. Yes. Huh? Yeah. Yes.
Oh, I have it.
I will look. I need a minute. All right, distance learners, I'll see you guys later.